Basically, what the previous part tells us is that we can approximate the optimal cut using the second smallest eigenvalue and eigenvector. And so far, we have discussed how to define a good partitioning of a graph. And basically one good partitioner is the one that can minimize a given graph cut criterion. And we also talked about how to efficiently identify such a partition. And the answer is to approximate it using information provided by eigenvalues and eigenvectors of a graph. And let's see how to put this all together to design a spectral clustering algorithm. Usually in a spectral clustering algorithm, we have three basic stages. The first stage is called pre-processing. This is very simple. It's just to construct a Laplacian matrix representation of the graph. And the second stage is eigendecomposition. Basically, we'll use eigendecomposition to compute the eigenvalues and eigenvectors of the matrix. And we'll map each node to a label or value in the corresponding eigenvectors. For example, we can map some of the nodes to here, some of the nodes to here. So some are larger than one and some are smaller than one. And the first stage is the final stage. We'll just assign these nodes to clusters based on the values or label. For example, we can assign all the nodes that have value smaller than 1 to one cluster, and we assign the other nodes which have values larger than 1 into another cluster. And more specifically, in the first stage, pre-processing, we will build a Laplacian matrix L of the graph. We are given a graph, right? And we have the corresponding adjacency matrix, and we'll compute the Laplacian matrix L using the difference between the degree matrix and the adjacency matrix, so D minus A. And in the second stage, we'll just find the eigenvalues and eigenvectors as of the matrix L. So for example, here we can use eigendecomposition to find the 6 eigenvalues of this matrix and the corresponding 6 eigenvectors. So each column corresponds to 1 eigenvector. And then we will take the second eigenvector, which corresponds to the second eigenvalue here, and we'll map the nodes according to this second eigenvector. For example, we map the first node to 0.3, we'll map the second node to 0.6, and we'll map the fourth node to minus 0.3, etc., etc. So the next question is, how do we now find the clusters given these tables? So in the last stage, we're going to sort the nodes of this reduced one-dimensional vector, and we'll identify the clusters by splitting the sorted vectors into 2. So how do we choose a splitting point, right? One naive approach is to split at 0 or the median value. For example, in the previous graph, we have a 10, this second eigenvector here, and we can basically split at 0, and we will put all the positive points into cluster 1 and all the negative points to cluster 2. So basically we'll put node 1, 2, 3 to cluster 1, and we'll put all the other nodes to cluster B. Of course, we have more expensive approaches. For example, we can attempt to minimize the normalized cut in one dimension. So the idea is to sweep over the ordering of the nodes induced by the eigenvector. For example, let's look at a larger graph, and let's say that we already taken its Laplacian matrix and we compute the second eigenvector, and we plot all the elements of this like 20 dimensional eigenvector here. Then one naive approach is that we can split this plot at this 0 point, which actually gives you a pretty good partition already. But one more expensive approach is that you can try split it here, 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 all the way to here. So basically you try splitting at each of this possible point, and you calculate the corresponding normalized cut, and you're gonna choose the one with the smallest normalized cut. And this is to ensure that your cut is actually gonna be corresponding to the smallest normalized cut. Let's look at an even more interesting example where we have a even larger graph of 40 nodes, where it has actually a subcluster structure. So we can see that we have these two large clusters, but inside each cluster we actually have two subclusters. So again, we'll compute its Laplacian matrix, and then we'll compute its second eigenvector, and we'll plot these 40 elements of this second eigenvector S2 into this figure. And we can see that it actually looks like something like a step function, where we can see that basically this node will correspond to this point, and this node corresponds to this point. And all these points actually correspond to this subcluster, and these points corresponds to these subcluster, and so on and so forth. Now, another question is, how do we partition a graph into k clusters instead of only two clusters? We have two basic approaches. One, of course, is to use recursive bipartitioning. So basically, we can just recursively apply the bipartitioning algorithm in a hierarchical divisive manner. But the disadvantages of this approach are that this approach is actually inefficient, and sometimes it's unstable. So another class of approaches is to cluster multiple eigenvectors. So the idea is to build a reduced space from multiple eigenvectors. And this is actually commonly used in recent papers. For example, a preferable approach is to use k-means. And for example, let's say that we have a graph of like four nodes, and we take the adjacency matrix, and we have the compute the Laplacian matrix, and we compute the second eigenvector as this column, and we compute the third eigenvector in this column, and the fourth eigenvector in this column. And then we can just use the first row in this matrix as the features for node 1, and the second row as the features for node 2, etc., etc. And then we can use these features to perform k-means clustering. So basically, the results of the k-means clustering will be the result of this graph clustering problem.